So, good afternoon, everybody. I'm Gabriele Luzzani, and I'm a PhD student from the Politecnico di Torino in Turin, in Italy. And I'm presenting the research that I'm pursuing in my PhD that is named Study and Development of a Real-Time Pilot Performance Monitoring System. Before starting, I want to thank all the authors that are collaborating in my research that involves different competencies merged together. For example, there is me and Nicola Puca and Professor Giorgio Guglieri from the Flight Mechanics Research Group of Politecnico. Then there is Irene Buraioli and Professor Daniele De Marchi from the Bioelectronics Research Group of Politecnico di Torino. And then Manuel Colavincenzo and Stefano Martorano from the industry partner of our project related to Leonardo Labs. So I decided to start this presentation by showing you this data that probably you know very well. So the fact that 90% of fatal accidents that occur in aviation are due to human errors. And it is possible to observe that the large part of them occur during the highest workload phases of a flight mission. So for example, takeoff or landings. And if we think about this data in the possible future transition towards the so-called single pilot operations, obviously these data are acquiring a more dangerous perspective. This transition is led mainly by two drivers. The first one is an economical driver, so the fact that it could help us to halve the operational crew costs, especially in short and medium flight routes. And on the other hand, it helps us to cover the forecasted pilot shortage that we are living now in Europe. However, to reach this goal, by following the EASA AI guidelines published by the EASA in 2023, we need to develop a collaborative and autonomous cockpit assistant named by EASA Human AI Teaming topic. However, it is due to the fact that it allows us to guarantee the same or higher safety and handling quality level regulated up to date in the EASA parts. However, to reach this goal, it is necessary to continue in real-time monitoring the pilot's state of health and his or her cognitive workload. And it is this the goal of my research project. Up to date, there are many free ways to assess the mental workload of a pilot during a flight missions. That is, the first one are subjective evaluations that obviously they lack of real-time capabilities. The second one are behavioral measurements that mainly are based on the comparison between an a priori defined mission plan with the actions of a pilot during the flight missions and infer from them the mental workload of a pilot. And then, last but not least, physiological measurements, as today a lot of people showed us, that are gaining more and more interest thanks to the development of the biomedical market in the last few years. And it is based on physiological measurements, our approach to the evaluation of mental workload of pilots during flight missions. In particular, what we are adopting is a multimodal approach based on the most adopted physiological signals in the literature that are eye activity, brain activity, heart measures, respiratory measures, and skin activity. We want to integrate this data with aircraft data in order to build a model that is able to infer a workload index from the pilot. In particular, what we are adopting in our research is the EDA, electrodermal activity, related to monitor the skin activity, the FNIRS, so the functional near-infrared spectroscopy to assess the brain activity, then respiratory measures by detecting the movement of the chest, heart measures based on ECG, and eye activity based on eye tracking. In fact, what we want to do is to acquire the signals, extract the most important features related to physiological signals, select them based statistical or machine learning algorithm methods in order to build a classification algorithm that is able, starting from these physiological signals, to infer the aforementioned workload index of the pilot in real time. So this is what we want to do, our goal. But what we did until now is this. In particular, we developed full flight missions on the A320 simulator that we have in Turin, the certified simulator that we have in Turin. We developed full flight missions from Milano Linate to Venice. And we asked the pilots to perform these missions in 3 different ways. A nominal conditions, then a nominal condition with secondary tasks. So essentially, we asked the pilot to answer to simple arithmetic questions during the flight that appear randomly during the mission. And then the last missions, that is a non-nominal conditions, where we inserted a failure on both the flight augmentations computer at the top of the end of the mission. So the pilot had to manage these situations, unexpected. And we divided each of these missions in 6 phases. So the baseline acquisition of the pilots, of course, at the beginning, then a taxi, takeoff and climb, cruise, approach and landing, so our full flight missions. And we were able to enroll 3 pilots, so an active ITA pilot, then a retired pilot that was flew A320 for all of his career, and then an amateur pilot that is certified to fly on simulators. And so at the end of each missions, we asked the pilot to fill an ISAE-TLX for each phase of the missions. So at the end, we had 3 missions, 6 phases, 3 pilots. At the end, 54 ISAE-TLX values associated to 54 phases overall. I acquired the physiological data using this equipment, the Biosignal Plugs Professional kit to assess brain, FNIRS, respiration, EDA, and heart activity, and Tobii Pro Glasses Full to assess eye tracking. And then in post-processing, I process all this physiological data to extract 98 overall features from the raw signals. Because, as I presented you before, we want then to select the best features that are better related to mental workload. In fact, the idea is to understand how these physiological features can be related to the ISAE-TLX values that we assessed from at the end of the missions. I remember the output of the ISAE-TLX values of the ISAE-TLX questionnaires is a single value between 1 to 20 that is evaluated for each of the aforementioned 54 phases. And as you can see here, I reported the trend of the ISAE-TLX that we obtained from the pilots, the different colors representing the different pilots. And as you can see, the data presents similar patterns between them, but what it is different is the range between the data, because obviously it's due to the subjectivity in the feeling of the data. So there is no homogeneity in the results. So I decided to perform a min-max normalization process on the 18 phases per participant. And what I obtain is that, so the fact that we can preserve the trend of the ISAE-TLX values, but now the data are comparable between them. And also the distribution that you can see here, what is, I don't know, okay. Anyway, the distribution that you can see at the bottom of the slide is showing a more Gaussian distribution of the data. So then what I did was to analyze each of the 98 physiological features that I extracted from the 5 physiological signals, and to perform on them, I mean, max normalization for each mission for each pilot to reduce the subjectivity among the participants and to avoid possible errors due to this. And so at the end, I obtained a dataset that was structured as in the bottom of this slide. So for each phase, it was associated an ISAE-TLX normalized value that is related also to a specific pilot and to a specific mission. For example, pilot 1, this was the normal condition and the ISAE-TLX values. And for each of the ISAE-TLX value, I had normalized values related to each of the 98 physiological features. Then, to analyze this data, the first step was to introduce a so-called binary analysis. So essentially, what I wanted to understand was the fact to understand which were the features that were able to discriminate from a baseline to emission conditions. So I divided the data set, as you can see here on the figure on the left, by dividing the baseline values that were put by default a value of 0 to the other features, and I performed a Mann-Whitney U-test to this different distribution for each feature. And as you can see, there are some features where the distributions are very well separated. For example, the figure on the left, and other that are not showing differences between them. And at the end, I obtained that the 30% of the initial features that I considered related to hot activity showed a significant variation among them. The significance was put with a p-value equal to 0.05, and the 50% for respiratory activity, and so on. So the result was the fact that more or less each physiological signals were able to discriminate a baseline from a momental workload condition. So I decided to do a step ahead, and I decided to split, moreover, the dataset in other two classes. So the low mental workload and the high mental workload. I did this by considering the median of the emission phases NASA-TLX values and to splitting low mental workload to high mental workload. The low mental workload was the NASA-TLX values comprised from the lowest value to the median of the distribution, and the highest, obviously, the other ones. And I justified this splitting by observing this graph. These graphs are showing the percentage of the phases that were related to the low mental workload and high mental workload condition. As you can see in class 1, that is representing the low mental workload, the highest values of NASA-TLX are related to cruise and taxi, so the green and the blue. That also from the comments of the pilot, they were the phases that were with a low mental workload, and the high mental workload, the highest correlated phases was landing and approach that were the highest mental workload, also by the comments of the pilots. So then, once obtained this division, I performed a statistical analysis based on this structure. So I performed, first of all, a Kruskal-Wallis test with a p-value equal 0.05 in order to understand if there is a test significance of the features. Then I performed a Mann-Whitney test between each paired of the classes. So class 0 vs class 1, class 0 vs class 2, and class 1 vs class 2, in order to understand which features were able to discriminate each paired comparison of the classes. And at the end, I obtained that 33 features, starting from the initial 98, were able to obtain significant statistical significance in at least 2 Mann-Whitney U-tests, and only 8 features were able to discriminate each paired comparison. And one important thing is that all of these features were related to skin, brain, and eye activities. I performed also a PCA analysis in order to understand if, also with a non-supervised algorithm, I could understand if inside the data set there were some patterns inside our data. And also this analysis showed that baseline, so the class 0 that is representing the baseline is very well defined, is very well separated by class 1 and class 2, while class 1 and class 2 are more merged together. Also, if by showing the 3D graph, they are quite, there is something that is differentiating them. Then the last step was to understand also if there is a correlation between the different characteristics. And so I performed a classical correlation analysis between the physiological data and the raw NASA-TLX values normalized, obviously. And what I obtained is that more or less that 49 features obtain a low correlation coefficients, 30 moderate correlation coefficients, and 19 high correlation coefficients. The important fact is related to the fact that as you can see here in the last table, I showed the percentage of features that demonstrated a correlation that is higher than 0.5 for each physiological signals. And I obtained that the same physiological signals that demonstrated significance from the statistical analysis also in this case showed the highest correlation values related to the raw NASA TLX values. In conclusion, I can say that these preliminary studies helped us to validate our procedure at the A320 simulator. And so these preliminary results are showing that the skin activity, brain, and eye activity are showing the highest correlation with mental workload in this specific case. And then that three-level scales for classification can bring reliable information that are also confirmed by the correlation analysis. And then obviously that we need more data to improve this preliminary analysis, also to try to build a machine learning algorithm that is our final goal. So next step, increase the population, of course, then try to develop a machine learning algorithm on them, put all of this in real time, and try to arrive to build the human AI teaming integration, the A320 simulator that we have in Turin. So with this, I thank you, and I'm happy to answer any possible question.